Hi, I want to talk with you right now about one of the fundamental tools in the realm of integration in calculus, which is approximating an area by rectangles. Integration is, in some sense, all about finding the area underneath a curve. And in order to do that, we use the computational tool of rectangles. So let's draw a graph and play with rectangles. So let's put a function down on this set of axes, and suppose that we're interested in a particular window from A to B, and I want to find the area underneath the curve inside of this window of interest. Okay? So I want to find this area right here. I want to find that area right there. One way to do it would be to just be like, well, it looks pretty rectangular to me, and be like, well, okay, fine. If it looks rectangular to me, let's take the area to be the area of this one rectangle. But you might be like, that's not so great. I think we can do better if we just use more rectangles. Why did you just use one? One's not good. Let's use multiple rectangles. And you're right. Let's use multiple rectangles. Why should we limit ourselves to one rectangle? Let's use 3 rectangles, and let's define them to be like that. Then I am going to define my 3 rectangles to be here, 1, 2, and 3. And now we should come up with a rule for how we determine the height of our rectangles. Now, I didn't tell you, but on that first rectangle that I drew, I used the left endpoints to generate the heights of my rectangles. So let's do that. All right, so let's draw my rectangles so that the left endpoint of my rectangle determines its height. This looks pretty good compared to our first one. We're like undercounting here and undercounting here and overcounting here. And so like that's, like what it is. I mean, we're always going to be a little bit wrong because we're using rectangles to approximate something curvy. But, like that's okay. What's so special about 3 rectangles? Why not we add more rectangles to our method for approximation? Let's say double that number and go to 6 this time. Let's say cut each of our rectangles in half and draw those. So let's cut in half here and draw more rectangles. Then I'm going to still use left endpoints. Finally, an overcount. There we go. Okay. So the area underneath the curve is now all well approximated by these 6 rectangles. But like 6 could be improved upon. Why not use 12 or 24 or 48 or 96 or however many you want, right? However many you want. That's what we should do. We should use a large number of rectangles to approximate this area well. Now, computers will happily deal with that. Us as humans, like I kind of top out around maybe like 10 before I start getting like I think this is too much work. Can I just have a machine do it for me? And the answer is yes, absolutely. A machine will happily do this kind of work for us. So I just want to say a few more things about approximating an area by rectangles before I call it good. There are various methods for determining height of our rectangles. I just did the left endpoint. There's also right. We could use the right endpoint to determine it, or we could use like centers. Or we could do a number of other schemes that we could come up with too. I'm going to content myself by listing these 3 things and then hinting that like rectangles could be improved upon by using trapezoids, but we're just going to stop and say it with rectangles. So you can well approximate an area underneath a curve by using rectangles, and we have a spectrum of choices for how we determine the heights of those rectangles as we approximate the area. Thank you for watching, and I will see you again next time.